Hey guys, today we're going to be building a Morse code translator using basic breadboard parts, a microcontroller, and a little bit of programming. So I had the parts before, and I stated them before at the beginning of the video. You need 3 resistors, a couple of wires, 1 LED. I'm using white because it's the brightest. Whatever you want though, you could use whatever. Uno R3. This tutorial will be on the Arduino Uno R3. You can use whatever you want though. So let's get started. Step 1, you guys already know what's up. We need to initialize power. Connecting from a grounding pin on Arduino to any blue pin on the slot, to any blue pin on the microcontroller. Just fix that for you. Can't zoom in. Okay, so first you have to connect a grounding pin on the microcontroller to a grounding pin on the breadboard. Then you take one of the really small wires, grounding pin on one side, grounding pin on the other. Do the same with positive, grounding pin on one side, positive pin on one side, positive pin on the other. So now you're going to create this arch. And let's take this red wire, connect. I'll use 3.3 volts because I don't want to fry any of my components yet. But if your components require higher amounts of power, use 5 volts. We will now get to the buttons. So we're going to be using one button for Morse code input, like we're going to press the button and that inputs into the Morse code, and the other one is just going to be adding spaces. And let's say we say something like S in Morse code, like dot, 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 and we want to do space, we could just press space. We need 2 buttons. Let's use the bottom one as space and the top one as input. Just move these down a bit, because why not? Alright, now you need one of your female to male wires and your male to male wires. You want to insert one end of the male wire into the female end of the female to male wire, like so. Make sure it clicks and stabilizes and stays stable. You don't want to push it in too hard, otherwise you could break it, especially if yours are like lower quality wires. Then the switches that I have connect diagonally opposite. So let me draw that out for you, if I can draw on this. Yes, there we go. So let's say that this is our switch, 4 prongs, and red is power, right? This is pink, but it is what it is. If power enters through here and the button is currently being held down, the power will exit from here. This is the kind of switch that I have, a press switch, a 4-pronged press switch. Probably can't see it because of the camera, but I'm drawing it right here for you guys. And when you press the button, it'll connect to it'll take power from the diagonally opposite end and spit it out the other diagonally opposite end. So let's just, how do I erase that? Nope, how do I erase that? Alright, let's keep going. I already told you guys to couple one male to female and male to male wire like this. Do the exact same thing with another set. Pick a long one. This is the long one. Let's just make sure we don't damage the wires, obviously. And now let's do the LED. Step with the LED. So the LED that I have has a longer end right here, shorter end right there. I'll draw it in more detail for you guys. LED here, one short, and in red, pink, one long. So The long stick takes positive power, and the short one will take negative power. So you always want to connect the short one to ground and the long one to a positive power source. So you want to connect the long one to the pin on your microcontroller, and you want to connect the short one to ground either via a resistor or just manually. I highly recommend you use a resistor so you won't damage your light or cause any fires, but you should be fine. Let me just... Okay, let's keep going. Oh, no. That's the LED, but we will put the long stick on the left side. So positive power comes in through the left and negative power will come in through the right. So I'm just gonna show you how I wired it like that. No, I'll show you how I wired it once I actually wire it. Gotta fix that. Quick fix. And put it in there. Other end. Let's use pin number 3. Use pin number 3. Pins in the coding process may be different than the pins used here, but you get the point. You can just switch around the pins. Make sure pin number 3 is your LED. Pin number 4 is the input button. Now pin number 4 is the input button. And pin number 6 is your... No, pin number 6 is your space button. This wire looks a little short. I'll be getting another one. Yeah, so I'll just swap this on out. Let's put this in pin number 6. And one here. Now, the reason I asked for 2 lower resistance resistors and 2 higher resistance resistors, 2 low and 1 high resistance resistors, is that we're going to need to do something here. So the lower resistance resistors we could use with the buttons. Put that in there. And directly to ground. In my opinion, connecting directly to ground is best with the resistor. I don't like putting resistors in the middle because it disrupts the flow of everything. So now we have resistors nice and neat on the sides, on my right, which is also your right. The right, nice and clean resistors. The back, you have this arch. But to abide by that cleanliness, let me just swap this around. Put this in here. Put that there. Once again, straight to ground. And I believe that is it in terms of building process. So I already have a copy of the code that we're going to make flashed on to our microcontroller. So I will just fix up the pins and let's test it out. Welcome back. Building was relatively easy, and if you missed anything, you could just rewind and check out those parts again. Now for this project, we have quite a large piece of code, so I'm not going to walk you through the building, but I'm going to explain you how the code works. First 9 lines, relatively simple. We define 3 variables, start, end, and a duration, to check how long the buttons have been pressed. This captures the start time, when the button begins being held, how much time has passed since the beginning of the program. Same with end, when the button is released, how much time has passed since the beginning. And duration, if you check down here, we do end minus start to get the duration in between. A transit is the amount of time between in between button presses. And found here, it's just saying was the letter found in the iteratable. And last button state is always set to high. Like at the beginning, the last button state is high because at the beginning of the code, the button state currently is low, so the last button state will be high. Current character, there's nothing being inputted at the beginning, so it's just blank. All the letters in the English alphabet, A to Z, and their respective Morse code. So if this is A, B, C, D, so on and so forth. Setup, once again, relatively straightforward. We set up a Morse light, the white light that I showed you guys. The general input, which was the one button that made the light glow, and the space input, which adds a space. Serial.begin 9600 basically initializes allow a communication between the Arduino and the serial monitor. 9600 baud rate. Loop. This block of code keeps looping on and on and on. Let me tell you more about it. So these two read the current state of the button. This top one reads the current state of the input button, and this one reads the state of the space button. So I decided to work with the space button first, and space is equal to low, which means if the space button is being pressed, just print out a space. Relatively straightforward. Reset the current character and do a 500 millisecond delay. If this delay were not here, you would be triggering the button a lot of times while holding it, because you're not holding it for only 1 millisecond. Your finger is pressing the button for almost 50 to 100 milliseconds, so you will trigger almost 50 to 100 spaces without this delay. But with the delay, you'd have to hold the button for 500 milliseconds, and most people are able to let go within 500. Feel free to increase this if you need to. Now this block over here checks if the button was not pressed before and is being pressed now. So if it wasn't pressed before and all of a sudden it just gets pressed, this block triggers. So it takes a start time in order to capture the length of the button press. Millis takes the amount of time since the code began. Digital write to high turns on our light, turns on our white LED. Transit is equal to 0, resets the transit time if anything was in there. And delay 50 milliseconds. Just so it doesn't keep repeatedly triggering. Otherwise it'll use up a lot of memory. Else if this is the exact same thing but in opposite. It's the same thing but in opposite. If the button was pressed before and is not pressed now, so let's say the button is being held down, but it's no longer being held down, capture an end time in milliseconds, again, since the program began, milliseconds since the program began, duration, end minus start, digital write to low, which means we're turning off the white LED as soon as the button gets released, and the transit time begins. The button has been released, so now we want to count the amount of time in between the button release and the next button press. And the amount of time the button has been released, which is transit, not between the next button press. Now, depending on the amount of time the button was held for, which is duration, DUR, we're going to do a couple of specific actions. And if it's in between 2500 and 3500, we're going to print out a dash. Common Morse standards, I think the American Morse standards say that it should be around 3 seconds for one dash and 1 second for a dot. But when pressing and holding the button, you're not going to press it for exactly 3000 milliseconds. You could be off. And I added a contingency, like a leniency of 500 milliseconds, like an error. So even if you're 500 milliseconds off this way or that way, you're fine. It'll still trigger the dash. Same thing here. 499, 500 to 1500. Adjusted for human error. Not all presses are exactly 1 second. It's explained right here. 50 millisecond delay. You just call this contingency. Just extra time being added. Else if transit is, now this part I'm going to explain you guys more in detail, just bear with me for a second. Else if transit is greater than 0, so the time since the last button press, so if the amount of time the button is being, the amount of time since the last button press is greater than 0, and millis, which is the amount of time since the code began, minus transit is greater than 3000, iterate through this list, find the character that matches, because we're adding the character. See here we add the character, we add a dot or a dash to the current character. iterate through this list, find the index. Let's say we input s, which is ... that is whatever index it is. It maps to s over here, and it will print out s. Iterates through everything. And now you may be wondering, why is there 25 and not 26? Well, arrays start indexing at 0, not at 1. So that's why the 0th position is actually the first position is actually the second, and so on and so forth. So the 25th position is actually the 26th. Then we change found to true, and reset the current character, and reset the transit time. Now, let me explain this. You may be wondering what this does. You have that. Let's take a timeline. Let's pretend this is the timeline of your entire code. Let's say, actually not yellow, let's do red. Say red is where the code started. The code starts right here. And the button is released right here. So this is where transit begins counting. So this purple stretch here will be the transit time. And this green over here is this part where it's been more than 3,000 milliseconds. So let's say green, 3,000 milliseconds. Over here, this is 0 milliseconds since the button has been released. It has just been released at this time. Purple is the time that the button has been released for. Millis, on the other hand, when using the millis function, it calculates the time from the start to the current time, which we don't want. This is what millis does. Calculates the entire timeline of the code. But we don't want that. We want only this little portion over here. So how do you do that? You can either employ a really complicated, memory-intensive way from C++, because Arduino language is based on C++. You could take a method from C++, or you could just do basic subtraction. So take this part, let's call this X, and take this part, this whole part, let's call this Y. If you want to come up with this portion, right, what could you do? Well, you could do y minus x. Y minus x is equal to portion. Let's call this P. We want this portion. That's exactly what we're doing in the code. Y, which is the entire millis, minus x, which is the transit time, is greater than 3,000. Yes. It takes the time since startup, so we need to remove the time before the button had stopped being held. You're essentially trying to capture how long the button was not pressed for. Keeping just millis, if you use just millis, will output the amount of time the entire board was active. Like the entire thing. I'm gonna link this in the GitHub if I can. And last but not least, last button state is equal to current button state. Which basically, the current button state, let's say it's currently being held, it's going to update that. So we could tell if the button was just being pressed or continually being held. This logic works better than just adding a delay because you don't know how long the end user is going to hold the button for. Let's say you make a product and sell it and give it to someone. You can't write only hold this button for 50 milliseconds. They're not going to want to use a product so with such stringent requirements. You need to allow some leniency, which is why this way is more common. I didn't use this method up here because obviously no one's going to hold a button for 500 milliseconds. That's half a second almost. Could change this to 1,000 if you really want to, but it's not going to do anything. I mean, it will, but it's not going to make that big of a difference. Now I'm going to test out the code. Okay, let's get back to work. Got my laptop there. Just move it so we get more space. I have power connected into my computer, the other one on the side, and we will get started. hide that. Okay, so we have all the code, and I'm gonna flash it one more time. 2, 3, and 8. I switched the pins, so pin number 2 is the Morse light, so this light. Pin number 3 is the general input, which is this button. And pin number 8 is the space input, which is this one. Doesn't give out a signal. Doesn't give out anything. So, without further ado, let's flash the code, see if it works. So now we have the serial monitor. We started 9600 baud rate communication. We told it to communicate at that frequency. So we set the serial monitor to this one as well. There are a bunch of other numbers. I just picked 9600 because it's the default for Arduino Uno. I think if you have an ESP, it's this one, 115200. Either way, let's get testing. Let's do something simple that everyone knows, SOS. That's ... .. Now, 3 seconds is what separate letters. So 3 seconds later, we get an S. Now, dots are usually 1 second long, and dashes are usually 3 seconds long. Between letters, it's 3 seconds. So let's do a dash, which is 3 seconds per dash. Should print out a no unless I typed it in wrong. There we are. Now, let's do dash. We've already done the ... and the ... Let's do ... again. Actually, let's put in a space for fun. Space. SOS. And there we go, we have a space. Now let's say we want to put in B, for instance, which is ... Let's put in a B, a space, and an S again, for instance. Should have printed unless I did something wrong. There, SOSB. Let's do SA, for example, or SZ. S will come out. Now let's do Z. Oh, I think I put an O instead of a Z. No, I'll put in a Z. So it should be SOZ now. There. Let's put a space and let's just do a singular dot. I think that is E. That is an E. Space didn't go through. There we go. Alright, thank you for checking out the video. I hope you guys enjoyed it. This project is one of the biggest projects I've done. There will be more, and they will be bigger, trust me. This is 64 lines of code and very basic building. So, thank you.